Hi, everyone. I hope everybody had a great lunch. So now we are starting our afternoon session of the Progress Workshop, and we are very happy that we have here today Dr. Yuejie from CMU. A few things about Dr. Shi. She received her PhD and MA in electrical engineering from Princeton and BE in electrical engineering from Tsinghua University in Beijing. And she's currently the Sense of Wonder Group Endowed Professor of Electrical and Computer Engineering in AI Systems at Carnegie Mellon University, with courtesy appointments in the Machine Learning Department and Scilab. Her research interests lie in the theoretical and algorithmic foundations of data science, signal processing, machine learning, and inverse problems, with applications in sensing, imaging, decision-making, and societal problems broadly defined. And she has received various awards, including the PICAS Award. She has been a distinguished lecturer of the IEEE. We are really happy that we have her with us today. And without further ado, thank you so much.
All right. Thank you so much, Dora, for the nice introduction. So I'm very happy to be here in Greece and to share some of our recent work with you. So today I'll be talking about how to accelerate your condition low rank estimation. The key word is to use preconditioning. All right, so we have a lot of data coming from also have sensors, computing platforms, imaging systems, and so on and so forth. And this large amount of data has brought lots of exciting opportunities. But in order to tap into these new opportunities, we also need new tools that sort of are efficient and scalable in their use of computation and memory. And fortunately, a lot of the data that we collect have low dimensional structures. I think for our community, it's probably not much needed for motivation that many of the data we collect has some sort of low rank structure where they can sort as embedding or encoding some latent structures where there's only a small number of interesting ones. So this kind of low dimensional structure kind of become ubiquitous across a lot of different applications we deal with across imaging, recommendation systems, community detection, bioinformatics, and so on. In this talk, we'll be thinking about a canonical problem that I call low-rank matrix sensing to start our discussion. So imagine you have some big data matrix M of size, say, N1 by N2, but fortunately, the rank of this matrix is small, say rank is R. Instead of directly observing this matrix, rather you'll be taking some sort of linear measurements of this matrix modeled by some linear map A, resulting in a collection of measurements M. Y that has dimension M. So typically, we'll be interested in solving this problem in the so-called sample-starved regime, namely the sensing budget, the number of measurements you have is usually much smaller than the ambient dimension of the matrix, but maybe just barely larger than the degrees of freedom of prescribing this low-rank structure. So we really need to leverage the low-rank structure if we want to solve this problem in a sort of faithful manner. And one intuitive approach is essentially trying to search among all the possible matrices and find the one that has the smallest rank that produces consistent measurements. Unfortunately, this kind of rank minimization is typically NP hard and impossible to solve. So there has been a lot of research going on trying to work around this by doing a convex relaxation. By instead of minimizing the rank, we can minimize the so-called nuclear norm, which is sort of the tightest convex relaxation you can come up for this kind of problem. And significant research has been put into this in general in the last decade, where we have been seeing a lot of nice statistical guarantees for this problem, where in many cases, this sort of convex relaxation solver can actually achieve near optimal minimax rate in terms of errors. However, this program is not necessarily scalable, because after all, this is a semi-definite program prescribed in terms of the ambient dimensions of matrix. So the complexity tends to be at least cubic with respect to the ambient dimension. And therefore, they have very terrible scalability when we want to work with large-scale problems. So in order to go beyond this kind of scalability issues, one resort to an alternative approach based on factorization. So if I know the rank of the matrix I'm looking for has some rank R, so maybe I can search among all the rank R matrices so that it has the smallest squared L2 error or least square error on my measurements. And this, I can directly tap into this low rank structure by rewriting this matrix C into multiplication of two tall factor matrices X and Y. And in doing so, I essentially rewrite the problem I'm interested in into an unconstrained optimization problem over the factor matrices X and Y. So the nice thing here is if you look at the bottom problem, this problem is much more scalable because we are only optimizing over these factor matrices that has complexity proportional to the degrees of freedom of the problem. But nonetheless, we now end up having a highly non-convex problem because this factors is actually not uniquely identifiable up to some invertible transforms. And speaking of non-convex optimizations, traditionally from the optimization perspective, they tend to be deemed to be somewhat tricky to solve and be hard in the sense, even for very simple problems that might be exponentially many bad local minima in the objective function. Nonetheless, in practice, people routinely solve these problems using very simple algorithms. So what actually saves the day, as we'll showcase at least in this work, is the statistical models come into rescue in the sense, rather than arguing about the worst case performance of our problem, we want to realize that actually often the data or the problem we are facing in practice are working on data that come from real life that are maybe drawn from some underlying statistical mechanism. So therefore, if you try to leverage these underlying statistical models beneath your objective function, instead of looking at all the possible realizations, you can maybe focus on average, what is the most probable construction of your loss function look like. And that turns out to be often much more benign, so that even very simple algorithms like vanilla gradient descent can actually be very efficient. So vanilla gradient descent in the most naive form will be simply trying to optimize our parameters along the descent directions of an objective function with some learning rate or step size. Indeed, this line of thinking has been very fruitful. So putting this back into this matrix sensing problem I mentioned earlier, one typical result people have is basically trying to solve this factorization objective function, often with some little bit help that try to balance the size of the two factor matrices called balancing regularization. And with this regularization in place, we can actually come up with a strategy that solves the problem in two steps. So the first step is trying to come up with a good initialization, typically based on spectrum method, that try to come up with a pair of factors that's not too far from the optimal point. But the initialization by itself is not a sufficiently good enough estimate. And once you have this initialization actually lands in this so-called basin of attraction, so that from that initialization, you can just run simple vanilla gradient descent, and that will hopefully give you good performance. So in this talk, I will not be focusing on the initialization part, but we'll just have to ask you to trust me that you can come up with good initialization for this problem. And this is kind of a warm-up kind of a result from the prior literature on the problem that's been developed a couple of years ago. So imagining you have this low rank matrix M that is rank R and has a condition number, which is a kappa that is a ratio of the largest singular value and the smallest non-zero singular value. And then for this counter sensing problem, you can actually show vanilla gradient descent achieve some epsilon accuracy within a number of iterations on the order of kappa log 1 over epsilon, as long as the sample size is fairly larger than the degrees of freedom of this low rank matrix up to some polynomial order with the rank and the condition number. So this kind of result actually has been established in the for many other type of low rank problems as well, such as matrix completion, robust PC, and so on and so forth. So it's probably fair to say that we have developed pretty good understanding about the performance of vanilla gradient descent for solving such low rank matrix sensing problem. Even though it's highly non-convex, we can actually get very nice global convergence results. So this seems to be all nice, but this is actually just the beginning of our investigation. One thing as someone who works on signal processing is that we know that a lot of the problems we are dealing with in real world are often yield conditioned. And in fact, if you take this very simple loss function for matrix completion, and you keep everything to be the same, but just changing the spectrum of the underlying matrix to vary its condition number, we see the convergence rate of vanilla gradient descent indeed degenerates quite fast at a linear rate with respect to the condition number. So that dependency on the condition number in the convergence rate is not an artifact of the analysis, but indeed is a real indication about performance degeneration of vanilla GD when you have bad conditioning. So a natural question we want to look at is, can we actually accelerate this? Before I actually do that, let me just give you a little bit more motivation why we care about condition number. Instead of going through all the possible applications, let me just show you one toy data example to illustrate this issue. So imagining you have some, maybe this is just data set I downloaded from some website that measures coloring concentration levels across 120 junctions over 180 time slots. So this is really just a data matrix of size 120 and 180. And indeed, as what we have been predicting, many of the data indeed have near-line structures, which can be manifested by plotting a spectrum in this decay form. So it has this so-called power law decay spectrum. So if I want to approximate this matrix using a rank 5 low rank approximation, this captures about 88% of the total energy and give me a condition number around 20. And if I want to capture more energy by doing a rank 10 matrix approximation, this gives me another condition number that is on the order 60. So this condition number may not seem to be terrible, but the key idea or the key message here is even for this very sort of innocent looking data, the condition number can be indeed very sort of larger than the rank or even comparable to the ambient dimension of the matrix. So in terms of the computation, we really shouldn't be ignoring the impacts of the condition number in our computation efficiency. Okay. So with this, this is sort of the question we want to motivate ourselves to consider: can we actually accelerate the convergence of gradient descent to a rate that's sort of independent with the condition number? Now, we want to stay with the first order gradient type of algorithm because we like all the nice things it brings in terms of, for example, machine learning, where you could easily have many distributed machines calculating local gradients and then doing global aggregation. So we want to stay with the paradigm of gradient descent type of algorithms, but trying to see whether we can actually accelerate convergence by getting rid of the condition number. All right, so that's sort of the question we want to answer. And in this talk, we'll be essentially examining this question in several aspects. We'll start with this sort of matrix estimation problem and give you a provable design that is insensitive to the condition number. And once we have sort of answer for that basic question, we'll try to generalize our analysis by looking at can we actually extend the idea to further develop algorithms that are also robust when the measurements can potentially be contaminated by adversarial outliers. We then want to extend to higher dimensional objects such as tensors and see whether this kind of idea can be applicable there as well. Finally, we'll actually try to go beyond this paradigm of having a spectral initialization and exact parameterization and try to understand, can we still succeed when the rank are potentially misspecified? So that's sort of our agenda. And with that in place, let me start with the first part. And this is joint work with my former student, Tian, who's now graduated and joined Amazon, and my colleague, Kong, from University of Chicago. All right. So this is our design, and this is probably the most important slide in this talk. we come up with algorithms that we call scaled gradient descent. And as the name suggested, we are essentially maintaining the algorithmic idea of gradient descent, but adding this sort of scaling or preconditioning into it. And we are not changing the spectral initialization. And we also don't need to add any balancing regularization. So we work directly with this vanilla least square laws. And what this algorithm looks like is essentially the following. So imagine you have two factors, x and y. You're going to update these two factors simultaneously. And if you don't have these red terms, these are just the vanilla gradient updates. But instead of doing vanilla gradient updates, I'm going to pull information from the red factor. Say I'm going to use y, construct y transpose y. So y is a tall matrix. So y transpose y is a tiny R by R matrix. So computing its inverse is not going to be expensive. In fact, often you can also combine it with calculations of gradient. So it's actually only adding a very small overhead to our calculations of gradient. And you are going to use this preconditioner to precondition your update for the left factor x. Now, similarly, you construct x transpose x, take an inverse, and use this to precondition the update for the factor y. All right, so that's the algorithm. And in fact, this can be thought as a preconditioned gradient method. If you vectorize your parameters, this preconditioner essentially pop up in the front of your gradient. So you can think of this also as some kind of quasi-Newton type of update. Now, how does it perform? Interestingly, when we put this on the sort of toy example we had before, we see that this new algorithm, ScaledGD, actually converge at a condition number independent rate. And all this convergence curve lay on top perfectly on the convergence rate of vanilla gradient descent, as if you have perfect condition number equals 1. But whenever the condition number is larger, ScaledGD is provably faster. So what this suggests is if you have a highly U condition problem, ScaledGD can potentially give you a huge computational saving by accelerating the convergence rate with only a minimum overhead added on top of each of the gradient computation. So the algorithm recipe seems to be very simple and seems to work. And you may wonder, why does this work, right? Intuitively, there's maybe several reasons, and this is kind of one of the nice intuition behind this algorithm. That is, this algorithm actually has some kind of nice scale invariant property. So remember that in this low rank estimation problems, these factor matrices are actually not uniquely specified. You can actually introduce, say, some invertible matrix Q, multiply it to one of the factor, multiply its inverse transpose to the other factor, that still give you the same low rank matrix. So from the representation perspective, you shouldn't be favoring one with respect to the other. However, if you're running gradient descent from either of these points, the updates can be actually quite different. You get very different trajectories of the algorithm. So the update of vanilla gradient descent can be very sensitive about how you actually scale these two factors. On the other end, what ScaledGD does is, if you take, no matter which factor you are taking, your next iterate will be actually covariate with respect to this change of parameterization. So if you change the parameterization as iterate T using some matrix Q, the same matrix Q will pop up in the next iterate. So in other words, you can essentially or almost think about ScaledGD as a manifold optimization algorithm, where it sketches out the same update in the low rank matrix manifold. And this is one of the key properties of this algorithm. And of course, to get really the convergence rate that we want, there's a lot that needs to be done in terms of analysis. And one key idea that is useful when analyzing this kind of preconditioned algorithm is that you actually need to come up with the new distance metrics to serve as a Lyapunov function to bound the sort of per-iteration progress of your algorithm. So this distance actually need to take into account as a preconditioning, and together with a very careful trajectory-based analysis. So with these ingredients in place, we can actually have a convergence guarantee for our ScaledGD algorithm for the same low-rank matrix sensing problem that will show this algorithm actually converge probably in a number of iterations that's on the order log 1 over epsilon. So it probably eliminates the condition number in the convergence rate at essentially the same sample requirement as the previous GD algorithm. So this is some sort of strict improvement over the prior results for vanilla gradient descent, because we essentially allow us to say computation without hurting the statistical performance. In fact, this recipe is quite general. You can apply this to a lot of other problems as well, such as robust PCA, matrix completion, and so on. And the message is also pretty similar, that essentially under comparable statistical requirements, we can probably improve the iteration complexity of gradient descent by eliminating the dependency on the condition number in the iteration complexity. Okay, so that's sort of our basic recipe for the estimating the low rank matrices by using this scaled gradient descent idea. And the natural idea to sort of extend this approach is to actually look at, can we also extend the idea to non-smooth problem? And this sort of also allow us to deal with the existence of outliers or corruptions in our measurement model. So let me explain this a little bit. So imagining potentially when you are taking this measurement pipeline, due to potentially maybe sensor failures or malicious attacks, maybe some of your measurements can be potentially corrupted by some outliers. Yeah. Yeah. So this result is for sensing. So, but we have also results for completion in the paper. It's just not, yeah. Yeah, it's in the paper, yeah. For non-convex is NR square, and that the square comes from spectral initialization. Yeah, because you need the spectral initialization. Yeah. There's no NR result for non-convex. Yeah, sure. All right, so this is a corrupted model where essentially introduce this outlier factor, which can be arbitrary, but we say only a small fraction of this outlier can be non-zero. So alpha here is a fraction of the outliers. Now, whenever you have outliers in your measurement model, the least square objective is no longer appropriate because you can have arbitrary corruptions. Nonetheless, we can actually result to the R1 loss, the so-called least absolute deviation loss, that try to optimize this objective function over that has this R1 norm form over the measurement residue. Now, the additional challenge when dealing with this problem is the loss function become additionally non-smooth. But nonetheless, the two-step recipe that we talked about earlier still more or less applies with some sort of specialized modification to deal with the existence of outliers. For example, in the initialization, you may need to do some sort of robust statistics guided approach. And in the local updates, instead of using the gradient, you may have to use the subgradients. But this approach suffers from similar slowdown due to yield conditioning. And as you can probably predict, what I'm going to do now is basically, instead of using the vanilla subgradient iterations, I'm actually going to add in my preconditioners here in basically the same manner. I'm going to precondition the left matrix using Y transpose Y inverse, precondition the right factor Y using X transpose X inverse. And typically with subgradient methods, your learning rate cannot be constant, but there need to be somewhat carefully set that some maybe polyic or geometrically decaying learning rates. And with this all in place, and turned out that we can essentially deliver a very similar message as a smooth case. And here it's just trying to benchmark our results with some of the previous results on subgradient methods, where for simplicity, I'm only highlighting the iteration complexity for problems such as matrix sensing or quadratic sensing, where again, we can probably accelerate the convergence by a factor of the condition number. So with this sort of subgradient methods, we essentially allow ourselves to solve this kind of low-rank matrix estimation problems with a robust property that is kind of double robustness to both underlying new conditioning of the low-rank matrix and also adversarial corruptions in your measurements. So we kind of achieve the best of both worlds in this setup. All right, so this seems straightforward. Let's now move to tensors. Now, tensors actually turned out to be quite interesting. And this is another set of paper jointly with Tian, Kong, and also my new PhD student, Harry at CMU. And we now have a lot of data that are sort of not just matrices, but the tensor data that are capturing sort of multi-directional, multi-way interactions of data across different modalities. By using tensor decompositions rather than trying to unfold this data into matrix forms, it is possible to capture this sort of multi-dimensional interactions and deliver insights that are not available when you are using matrix methods. So there are actually a lot of interest in looking at tensor data. So similarly, well, so for tensors, there's actually not only one possible way you can do a low-rank decomposition. Now, in this talk, I'm going to take this so-called Tucker decomposition that's defined by this very complicated looking equation that I don't want to get into this definition, but pictorially, this is really what we are trying to do. Instead of representing this high dimensional tensor directly, I want to represent this using 3 tall matrices, U, V, W, each kind of tell you the subspace of the data that belongs to in that dimension. And we have this very small, tiny core tensor in the middle, where each of the dimension can be thought as the rank along each of the modality. So instead of directly estimating the matrix T, so the tensor T, we'll be thinking about estimating this factor matrices and the core tensor. So this is another sort of multi-linear representation, right? While in the matrix case, we only have 2 factors, but now we have essentially 4 factors that we are dealing with. All right. And the sort of the canonical problem here, again, is this kind of low-rank tensor recovery problem. That is, given maybe some linear measurements of the tensor, I want to be able to recover this tensor. And surprisingly, tensor problem seems to be much, much more challenging than its matrix counterpart. And some of the potential reasons might be the following. So the first one is computational hardness. So we know that for matrices, we can result with convex relaxation, such as a nuclear null minimization. But turns out that the convex relaxation for tensor rank turned out to be NP hard to compute. So even you do convex relaxation, it doesn't mean you can solve it in a computational tractable manner. So it's also a wide belief in terms of the so-called computational statistical barriers by connecting this to some sort of hardness conjecture people have in computation complexity theory. It is believed that you can only come up with polynomial time algorithms for tensor recovery when the sample size is above the order of n to the 1.5 order. And in fact, if you count the degrees of freedom of the low-rank tensor, it's only linear in n. So this n to the 1.5 order is strictly above the number of measurements you need to prescribe the tensor in an information theoretic manner. Finally, when we start working on the problem, there seems to be very little existing results for the Tucker case. There has been some results for example, the case with CP decomposition. But for the Tucker case, there is actually no provably efficient first-order algorithm for low-rank tensor completion under Tucker decomposition. There is one nice paper by Willard et al. Where they look at the sensing problem using gradient descent that I'll also mention a little bit later. So this is sort of our goal. And we want to actually look at this problem and generalize our idea of designing scaled gradient for tensor problems. And how to do this for tensors? It's not immediately clear, but we know how to do it for matrices. So why don't we maybe try to unfold our tensor into a matrix form? So if I unfold my tensor maybe around the first mode, this actually allows me to write this as a matrix multiplication, where the left factor is U, and the right factor actually write up all the information from the other factors. Let's say I call U brev. So if I want to write down the scaled gradient update for the factor U, I could just think about this as a matrix thing, and where the preconditioner is going to be designed using information from U brev. So I just take U brev transpose U brev inverse to precondition it. So I can actually do this for all the factors UVW. There's one last thing, that is how to update the call tensor. And that I can't directly use this intuition, but it turned out that this is something about the invariance and properties. So that actually this is how we want to update the call tensor. Okay, so if you put this together, you get this very complicated looking thing for the algorithm. This is kind of unavoidable working with tensors that once you raise the dimension, the complexity notation actually also scales exponentially. But again, the key property is with this update rule, we get the similar kind of invariance property with respect to parameterizations of this factor UVWS, where if you think about all the invertible transforms. All right, so with this algorithm, we actually show the performance. We show in the paper, we show both for sensing and completion. So here I'm actually showing the result for the completion case. And again, the key message is we were able to get result where the computational complexity is on the order log 1 over epsilon. So probably independent with condition numbers. As long as the sample size is on the order of n to the 1.5 order up to some polynomial factors with other things. So again, this actually gives you the first probable linear convergence at a near optimal sample complexity for this kind of problem. Now, if you look at the performance, this is basically very similar to the one that we've seen for the matrix case, where the convergence rate of our ScaledGD algorithm is very fast. Well, if you run the regularized vanilla GD algorithm from the previous paper by Willard et al. For this completion problem, even though they don't show guarantee for completion, this algorithm actually also suffers from performance degeneration with a condition number. Now, in fact, if you plot the convergence rate as a function of the condition number, the convergence rate for this tensor problem for vanilla GD actually depends quadratically with the condition number. So you actually suffer even more with bad conditioning when you're working with higher dimensional objects. Well, our algorithm actually has a constant scaling regardless of the choice of our condition number. So the benefit of using this kind of scaled updates is more evident when you are working with tensor or higher dimensional problems. All right. I don't know how much time I have because we sort of lose some time in the beginning. Okay, good. Yeah, so well, I'll actually skip this. Maybe I will say a couple of things. Okay, so we actually also work on this sort of tensor problem on this application called robust PCA, where you can essentially generalize the ScaledGD algorithm design to additionally handle corruption and outliers in your tensors. And one interesting thing I want to show is actually this sort of connection to maybe some of the neural network and deep learning things. That all the algorithms that I've developed so far is kind of nice theoretically, but when you actually implement this algorithm in practice, for example, this RPCA algorithm, there's tons of tuning parameters in the algorithm in terms of how you want to tune your learning rates, how you want to construct some maybe thresholds to remove outliers at every iteration. And those are not necessarily easy to tune. So my student Harry came up with this approach that he basically takes this unfolding view of this kind of iterative algorithm and leverage the sort of self-supervised learning technique that does not use underlying ground truths, but just the incoming data alone to help to tune this hyperparameters in sort of a self-supervised way. And without sort of really much efforts, maybe with some efforts of the GPUs, we show that actually this approach delivers quite nice recovery guarantees when we apply this to some materials data set, where we can actually quite nicely separate a low-rank component from some of the saliency factors that our collaborators seem to have quite meaningful for their application domain without actually using any domain knowledge. So Harry will actually going to be presenting this paper at ICASSP, I think on Friday. So if you're interested, you can go through his presentation to learn more. So finally, let me just quickly talk about the last aspect about having overparameterization in this approach. So for this, I'm going to actually revisit the matrix setting because it's sort of easier to set up the stage. So far, I have been sweeping importance under the rug. That is, I'm assuming secretly I know the rank to use for my problem. And in fact, if you do not know the exact rank of the low rank matrix, this approach may fall apart in the sense, so if you do not know the exact rank, then what you could do in factorization is you overparameterize. So instead of using the rank R, you parameterize using maybe some higher rank R prime and trying to recover this fatter factor matrix X using this kind of ScaledGD update. So this is for PSD case, so there's only one factor. And when you have overparameterization, this factor matrix itself could become U-conditioned, so that this inverse, this preconditioner, become actually potentially unstable. And in the analysis will also break up. So in order to fix this issue, what we can do is kind of similar to what we usually do with regularization, Tikhonov type of regularization, is to add some identity matrix in this before we do inversion. And this helps to stabilize the preconditioner and make the algorithm stable again. So this is actually also connected to a lot of the observation or discussion people have in deep learning, because once you overparameterize, we actually have infinite many global minima. So we can actually overfit the data, so the training error is always 0, but not all the matrices that are consistent with our observations are the low-rank matrix we want. So there's a separate question in terms of generalization. Can we actually guarantee generalization here? Now, this is particularly interesting for preconditioning because preconditioning is originally sort of considered or motivated to accelerate computation. But by accelerating computation, we do not necessarily know whether we are still converging to a solution that is generalizable. Are we accelerating but overfitting, right? So that's the question that's not clear. And in fact, this kind of question has been attracting a lot of attention in the machine learning community, where they try to study how preconditioning, whether how or hurt generalization. So our study here can also be thought as trying to answer this question, but for this kind of low rank estimation problems. And surprisingly, the answer is it actually does not hurt generalization. And indeed, we show that if you do the sensing problem, if you pick your regularization, your lambda, as on the same order as a minimum non-zero singular value of your low rank matrix, and then if you use a very small initialization, a small random initialization, then you can actually guarantee that you also get epsilon accuracy within this number of iterations at sort of a comparable sample complexity as before. If you have exact parameterization, this analysis actually also gives you perfect recovery when you are just using random initialization. So let me try to pass this convergence rate a little bit using a figure. So earlier, for this kind of low rank sensing problem, there are also analysis done for gradient descent. And roughly speaking, both of these algorithm has this kind of two-stage convergence. Whereas the first stage is essentially somewhat like a feature learning stage, where you try to figure out the low dimensional subspace for a low rank matrix. And this part actually takes a complexity that's polynomial with a condition number. And once you sort of learn the features, you enter into the nice local regime as we showed before, as if you have spectral initialization, and you get linear convergence. But actually, the dependency with the condition number is also worse. On the other end, with ScaledGD, we actually have this initial phase that only depends logarithmically with the condition number, ignoring some log dependency with the dimension. So in practice, often we actually hardly observe this stage. The algorithm often almost pick out the feature space in the constant number of iterations and converge. And once you learn the sort of the signal component, you will get back to the stage of local convergence and converge linearly at a condition number independent rate. So again, even in this overparameterized settings, our ScaledGD algorithm it allows us to pick up the signal component at a much faster rate than GD from small random initialization. Yeah. Yeah, all these results depend on kappa, even for the earlier results. And this is kind of an analysis artifact. Even for vanilla gradient descent, the sample complexity has kappa. So for all the non-convex analysis in the literature, the dependency with R, as you pointed out earlier, is not optimal. And also there's dependency with condition number. Yeah. Yeah, so empirically with either GD or SGD, so ScaledGD. So the main difference of this algorithm is computation. In terms of sample use, empirically, they do not seem to be relying heavily on the condition number. Theoretically, yes, that's what you are seeing in all these results, in all the non-convex results. Yeah, for all the non-convex analysis. All right, so let me conclude quickly. So in this talk, I've been highlighting this approach that sort of advocating this preconditional design for low rank estimation with the hope that to accelerate yield condition, the convergence in the yield condition case. Across the board, our hope is to design algorithms that are statistically near optimal in terms of sample use. Also computationally, that can achieve near dimension-free iteration complexity in terms of both problem dimension and the condition number, and has additional robustness with respect to adversarial outliers in yield conditioning. And we see that the key idea underneath a lot of the analysis is to explore the additional problem structure and geometric property associated with these low rank estimation problems, and go beyond just analyzing convergence of optimization algorithm using a black box approach by carefully addressing how the iterates progress along different iterations. And again, finally, we see even very simple variants of gradient descent allow us to achieve much faster and robust convergence compared to its vanilla version. And if you are interested, okay, so this is my slogan, preconditioning helps. You should try to think about how to design preconditioners for your own problem. Gradient descent often is very painfully slow. And right now we are actually trying to generalize this idea also to other problems. For example, one is the asymmetric case for the overparameterization setting. We are currently writing up the proof. But we are also leveraging this idea to other learning and estimation problems, such as spike deconvolution, super resolution. There are many potentially interesting directions to go. All right, so these are some of the publications we have, and I'll be happy to answer the questions. Thank you so much for your attention and for having me here. All right. So if there are no questions, I guess we're done. And feel free to ask me questions if you have other questions offline. Yeah.
Okay, thank you. I wanted to know is the condition on the rank for every iteration maintained?
Yeah, you use the same rank.
Do we always get it, or is it dependent upon the structure of the function or the gradient function?
So the rank is like an input parameter, right? If you know the exact rank, you can use the first version without overparameterization. If you have some, if you generally, so this is actually a tricky question in terms of rank selection, right? For running this algorithm, it kind of depends on the problem, because generally speaking, your data may have maybe a spectrum that look like this. So you could argue that you don't really have exact parameterization. There's always a U-conditioned matrix, but this U-conditioning by itself can become very large if you do not add in the small regularization in the preconditioner. So at the end, that's some sort of design choice.
So in the gradient, in the iteration you gave, the equation where you do the preconditioning, is this the function f of xt yt, right? That
yeah, so f is this.
Right now, that is the cost function. Suppose I change that cost function.
You just update.
Can you maintain that the rank of yt plus 1 will remain the same as rank yt?
They will have the same shape, right? But if you have overparameterization, they can potentially become less stable, right? That's why you need to. They can potentially become rank deficient or close to rank deficient. That's why you add the lambda I in the preconditioner.
Okay.
Yeah.
Thank you.
All right. I think we're done. Thank you.